Is this presenting? Oh, yeah, perfect.
There we go. Hello, everyone. For the last talk before lunch, VAPI is a community sponsor. Thank you very, very much for sponsoring. We're going to hear about AI.
Yes.
That's all I'm going to say. And I'll leave you to kind of introduce yourself. And yes, AI.
Super excited to talk about AI.
Thank you.
They had a little fun with my hair on the mic. Yeah, thanks for being here, and thanks for listening. I didn't know exactly what to talk about. This is a super interesting crowd. I'm learning a lot about transports. There's a lot here to talk about, like with ML engineers, but I wasn't sure what would be interesting. So the material is really on like 5 minutes, and I'm hoping we can just like dive into whatever curiosities you guys might have. I think there is a lot of interesting things happening to set like a high-level overview. The things that you were talking about with like WebRTC was this like wave in like 2011, and now I think there's like media real quick that I'm hearing about. Like a lot of details to get right to make magic happen across the internet. And there's like similar amount of details that you need to get right now with GPU programming and these models. And I think maybe that might inspire some of you to shift work towards that. So I just put the title as that's 500 milliseconds, I guess, is the high-level goal that we talk about at WAPI. And that's just how fast, I guess, like humans turn take. In a conversation, people can actually turn take like even 300 milliseconds, but 500 milliseconds is like the golden, I guess, benchmark people talk about, where if you have this fast, it should feel human that you're talking to when you're talking to a bot. So let's just get into, I guess, the history, the Paleolithic man of voice bots. You have a user talking to one of these older systems, and they're talking, and they might pause. So they pause for, let's say, like around 500 milliseconds. You have a VAD system or some other way to detect if a user is done speaking. You might process, you detect like, okay, they're done speaking, let's move on. You try to like maybe transcribe what they said. That could be around another 500 milliseconds. And because these are older models, they were not like transformer-based architectures. So that added additional latency to these things. And then you try to get a response, obviously, which is like, okay, now we have the user query. What should we say? You could have a full dialogue flow. You maybe have like some of your own entity detection, mapping it to some response, some NLP stuff going on. And you finally get some speech. This again, you could maybe have a lookup table mapping to a response, or maybe you generate it on the fly. And in the end, you get kind of like 2,500 milliseconds is the rough, I think, estimate people give for these older systems. So now, I guess, we look to the future. The future has already been with the past. So when I guess I originally was thinking about this presentation, the world had not seen GPT 4.0 and how incredible that was. So this slide is more about, I guess, the interim of the last years, like systems were like. And you again have a user talking. And as the user is talking, as I'm talking, you're probably thinking about something. You're processing what I'm saying. So in your head, you're transcribing maybe to text. Something like DeepRAM is super fast. They have a real-time factor of like 500. So within 100 milliseconds, you know what the user is talking about. And once you know what the user is talking about, maybe there's like, I'm hand-waving a little bit of logic here. So you know what the user is saying. At some point, maybe you in your head are thinking about a response. And kind of the same thing, you can design a system where you're constantly like taking these like streaming transcripts and like trying to come up with a response. And if you have a text response ready, maybe you can also have like a speech response ready. And there's, I guess, one little detail to highlight here, that these newer architectures based on transformers, that fundamentally they lend themselves to a streaming because you have next token prediction, or you have next audio token prediction, and that means you have the transcripts coming in, you have the response coming in, but as the response is being generated, you can actually synthesize it into speech. So end-to-end, these things, if LLM within 200 milliseconds, you should have something that you can start speaking, and then speech synthesizers, there's quick ones that can do within 200 milliseconds. So this is happening while the user is speaking. And at some point, the user does stop speaking, and then the bot comes in. So then you have, your 500 milliseconds golden number. Of course, in reality, this doesn't happen all the time. And there's, maybe some of you might have read about the old literature with CPU, it's in 1980s, and they had to and compilers, they had to learn about branch predictions and branch failures. It's kind of the same thing here, where your user speech is coming in, you're predicting a potential response, but some of them you might run into branch failures, and that's all good. But as long as when the user is actually done, in this VAD could actually be potentially a smarter model to know when the person is done speaking, and then you can just swoop in with your speech. So far, any questions on any of these pieces? No. Okay. So then I guess we looked at the bit of the future. I guess this is where a lot of the interesting work is happening, and I wasn't sure how much, what would be interesting to this crowd. So I just kind of left it pretty open-ended, and we can dive into any questions you might have, or any potential interest you might have. But what's really going on now is you have these end-to-end neural networks. Because as I'm speaking, there's a neural network potentially going on in your head that's taking these audio chunks, discretizing it at some resolution, and making a prediction whether to maybe interject, maybe interrupt, maybe keep listening. These audio chunks, maybe when you, as they go through the neural network, they decide hey, I want to actually start speaking, I want to fully interrupt this person, and then you go through a bigger chain, bigger neural network to produce a response. And these things can happen within so 80 milliseconds is roughly what I put, because when you look at maybe 7 billion parameter models, you can get around 30 to 40 tokens per second very easily. So this is an upper bound. And 20 milliseconds I put because that's the chunk size that you can get on RGP or other protocols as well. So you have user chunks coming in, and they're directly conversing with the GPU. The chunks go into the GPU, you run some inference on it. Maybe you decide that we're going to keep listening, there's nothing more to do here, or you decide to interrupt. And that's maybe gets you 100 milliseconds or something crazy, where you're conversing directly with these things. And that's kind of what the GPT-4o demo was about. If you haven't seen it, I do recommend it. And they, I think, put their model as around 400 milliseconds end-to-end, which is super quick, and for a model that smart, but it's totally, I can see how they would achieve that. So that was my prepared content, and I didn't I guess this thing that happened with GPT-4o was only 3 weeks ago, and kind of shifted my plan for what I wanted to talk about. It shifted our plan for how we make voice bots. And yeah, it's very open-ended. There's a lot of curiosities people have around different architectures that they're using. I can go into any depth into any of those approaches if you're curious. But that's, my prepared content. So what would be interesting, if at all, to talk about? We can take open floor.
Has anyone got any direction they want to steer the conversation in? Yes?
Okay, I'll give it direction that is interesting to me. So these do you think there's opportunity to, like if you're into a conversation,
100%.
obviously you can't do this in the beginning. Is it possible that can you use more predictive kind of like generation so that you can guess what the person's about to say, like, because we do this in real person speech as well, like, oh, I know what you're going to say, like and then you just have some filler words or whatever towards the end of what you're trying to say.
So that kind of architecture is what we were building with like the old system, where you're potentially predicting someone's responses and then having a response ready. This actually gets completely rid of that, which is interesting because maybe I can talk a little bit about how the best guess, I don't have any privileged information, but like how the best guess on like GPT-4o, like these audio speech-to-speech models are structured. So you have the audio coming in, and you have an encoder network, which is like audio, taking these audio bytes and converting it into an audio token. Audio token we don't know exactly, of course, like what the semantic meaning that these audio tokens capture, but you can imagine like laughter or like the tonality that exists. And these audio tokens are then, so they do this for different modalities. So you have audio, image, video, and you get all of these different discretized like tokens for the world so far. These tokens are then, I guess, but once they're in one token space, you can go through another deep network to get a generation on the other side, which would be like the end token, I guess, from that. And then you used to use, I guess, like an embedding matrix, but like in this scenario, like for text tokens it's easy, right? Like text tokens map to like specific words like spi, chu, like those might be different tokens in text space. Of course, like audio is a lot more complex. Like how do you convert an audio token back to like audio waves? In traditional speech models, like text-to-speech models, you would have a vocoder that would like take these audio, they take these text and produce like audio waveforms out of it. What the best guess that people think that they're doing right now is they have a decoder network. So you have an encoder network which goes through this deep network, and then you get these audio tokens, and then you decode them into different modalities, which might be audio and text. That's kind of the basis of what we're working with. Now, my best guess is like how backchanneling or interjection is going to work is you have these audio tokens that come in, and you don't go through the deep network immediately. You can have a shallow network where these audio tokens are, of course, very rich information. They carry a lot of rich information on what the person is saying, how they're saying it. You can have a shallow network that takes these like special, very meaningful tokens and makes a prediction on whether I should keep listening, whether I should start talking, or whether I should backchannel. And then you don't need to have a response ready, I guess, all the time. I guess like when we in our head, like I guess like thinking those like subliminal thoughts as someone is talking, that's what I think of as shallow network. And then we actually articulate, that's like the deeper network. And that's what I meant with the GPU programming, because no one knows like the details of this. No one has ever made a system that compelling. Of course, OpenAI is working on it. So if you guys want to move from transport layer to the application and GPU layer, it's a good time to be alive. And a lot of interesting work being done there where, you have these models. They're all part of the same network, but then you can exit at different points, basically. And it's just one GPU that's active. That's another thing that's interesting in this. Maybe that'll be interesting more towards the transport folks, is the world, I think, of distributed system was designed with like statelessness in mind. This fundamentally breaks that architecture, where like you have to be talking to the same GPU, because maybe that's one thing I didn't mention there, is this 80 millisecond can only happen because they have the KV you have the activations hot from the last generation that you did. So you have this network. Similar to on your mind, when in the GPU, you're talking, the new 20 millisecond chunk comes in, you already know what generations you had for the last 20 milliseconds chunk. So everything is super hot and super active, and all you need to do is add this 20 milliseconds and need to go through, get the attention for basically this 20 milliseconds and make predictions on that. So the architecture is going to look very similar to, I guess, like how internally subliminally think about thoughts and then finally articulate it. Is kind of how I'm guessing right now it will go, but it will all be in GPU, one GPU.
As with networking stuff, there's a latency, sort of a throughput time to first token trade-off here.
Mm-hmm.
Can you talk a little bit about how you think about like scaling this stuff up and the cost trade-offs as you have like a lot of users sharing this kind of infrastructure?
Yeah, so that's going to be super interesting. I think there's like two solutions that are coming in. One is like on device, right? Like you're just talking to like your iPhone, which is not crazy because if you look at Apple's presentation yesterday, their local model can run on at 30 tokens per second, which roughly also maps to like around 80 milliseconds, right? Like humans don't, like when we turn tick, we do not turn tick faster than 200 milliseconds. So it's within the bandwidth of a human. So for a 3 billion parameter model, maybe in future, if you imagine like scale that up with Moore's law, like 10, 20 billion parameter model, it's likely you'll be talking to your computer, like device like directly. And again, the architecture is just, it's keeping the activations hot. Every 20 milliseconds is going into the network, making a new prediction, exiting a different point. So that's, I guess, on device, or that's the one cheat code to solve the network and throughput latency, just like do everything on device. So a lot of GPU networking stuff that's happening is very exciting on the device. Now the second thing that's happening that's exciting on the data center side is memory. Because the things that I'm talking about were to keep, this is rumored, no one knows what's happening, but when you're talking to ChatGPT, it's very likely that they're like, when it goes to the cloud, the activations are like flying across GPUs, basically like these, it's just, imagine like your brain, my activation is just like ran in your hardware, like it's just like some weird sci-fi, like just consciousness moving around basically, like these activations moving around where, so yeah, the context of what the conversation was, as long as you have enough memory, is going to stay in those GPUs. That is it, yes. That's basically what it's getting to.
Can you repeat what?
Yeah, the question was, so does that mean there's a shared KV cache? Yes. Which already happens, yeah, and there might be a shared, I don't know if you guys saw NVIDIA's GTC presentations, but like Jensen is very big on, here's my 1 GPU, here's my 2 GPUs, here's my machine, and here's my AI factory. And he's like, this AI factory is one giant GPU. Which is quite literal because this AI factory, I think, the bandwidth between these systems, between these GPUs is like terabytes. And they're going to keep pushing that up. And the reason they're pushing it up is because they need, if you want to have 1,000 people talking to these, the same model code, you can keep their KV caches, all of them hot, and then do a batch processing. Sorry, I'm now super theoretical and I've probably lost a lot of people. But basically you have the shared KV cache, 1,000 people are coming, 1,000 people are sending like every 20 milliseconds, like these audio chunks. You align them at some point, maybe you align them at like 30 milliseconds or something. You get all their activations and then do a big inference run, and then on to the next one, on to the next one. That's most likely. And again, it's not been perfected. These are systems that are being designed right now as we're talking about. These algorithms are being written right now. So a lot of fun stuff. Yes?
The 80 milliseconds GPU time, is that NVIDIA GPU?
That's NVIDIA.
Or is that, are you working with other GPU vendors? What makes NVIDIA GPU better than the others in your experience?
I think NVIDIA GPUs are very programmable. They just have like such good ecosystem, is what that comes down to. So the thing I'm talking about, like if you want to try to have a network and like exit at different points of the network, one giant network. Like the most like complete language that exists to write that kind of future in is NVIDIA GPUs. Of course, it will be very exciting, and I'm sure there'll be newer abstractions, like kind of the same way where Linux, I guess, like is written in C and is pretty tied to the kernel. But then, I guess, like compiler for C came out, like the LLVM, I think, and then now LLVM compiles C to AMD as well. So at some point, Linux also could run on AMD. RISC or other different architectures. So I think basically what's going to happen is I think at some point these programs that you write will be able to compile down to like any different type of GPUs, whether that's AMD, whether that's Grok, whether that's any new architecture. But for now, yeah, like they just have such a lead on like the ecosystem that support them.
I have two questions for you.
Yes.
So, are we in danger of the telephone networks we view as incumbent because they are a monopoly for the most part? Are we in danger of getting into an AI monopoly? Before you could have a speech-to-text provider, and then you could go with the best one, and then you could go with the best AI provider, and then But now we're kind of getting into, we have to stick with one, and ultimately, they don't do voice cloning as good as this other provider, but we have to stick with them because the whole audio speech-to-speach.
That's the setup, yeah.
Are we in danger of getting into incumbentness again? And then, as a follow-up question. Open source solutions were getting pretty good at those three individual things. Are we again kind of restarting the clock on not being entirely reliant on an AI platform, I'm going to call it? Have we kind of reset the clock again?
Yeah, that's super interesting, and I don't know. The first question actually, you mentioned telephone providers, and I had an interesting thought there as you were speaking about it, where it's a great moment to be in transport, like Media over Quick or WebRTC, because the network, like the volume that's going to come on these transport is going to probably 10x as like these things get really good. There's no reason why you would talk to AI over like the PSTN network. You can probably go over the internet, and so the usage of these web transports are going to get massively, I think, increased. We'll see, but that seems I don't see any reason why it wouldn't. So that probably erodes like telephony providers' monopoly, which is probably good. On the side of like these model makers. I kind of mentioned how like on-device seems very, very likely. There's no reason why that wouldn't be solved. And yeah, like open source seems pretty compelling. Of course, like there's no one who has a very compelling like speech-to-speech model out there in open source yet, but I'm sure that'll come. And the reason no one has it is the investments to make these things are in tens of millions, not like thousands. So we're all kind of just waiting for like Meta to like open source something that's like compelling, then we can go play with it. And I wouldn't be surprised if majority of the usage that exists in AI is not OpenAI, because it's like trivial tasks that I just talk to my device for. But OpenAI does have like a monopoly on the smartest models, and like for the smartest models, we're kind of the same thing where like you guys are experts. People come to you, but for very specialized things, most people can like find a lot of information they need on the internet, right? Or they can use like the transports that you make. So like OpenAI models will be super, I bet, compelling, but they're probably gonna. The only thing I can see that they will securely keep is the specialized, like the hardest tasks, whereas like all these lower end majority tasks are going to keep getting commoditized by open source, by other solutions. So unlikely to me that like majority of the world. Yeah, it's very much a path to commoditization that's happening. Yeah.
I think there is one more layer there, translator, like language translator also is there. It's able to detect the switching in the languages, like we can actually switch from English to French, French to German, and come back to English. It's able to collect all of them and able to answer it back, actually.
Yes, yeah. That's a crazy thing. Like this brain is like this, as these brains get better, it'll be no different than talk to a person. If a person is multilingual, these models can be multilingual, and they already kind of showed a demo of that. Again, if you saw the GP4 demo. So yeah, you'll talk to it, it will understand it, it will respond in whatever language you need it to. Of course, there's a lot of use cases that this speech-to-speech paradigm doesn't cover, right? The agent assist and stuff. This is purely about how would humans get support in the future. Yeah.
We are out of time. Thank you so much for that.
Thank you.